Okay, and I'd like to take some time to just walk you through one of these codes, in particular the Simpson's 3/8 rule. I'd like you to be able to modify this code to complete a replica of Boole's rule. Okay, and now there's some interesting things going on here that are unique to Matlab, but remember that for Simpson's 3/8 rule, there's this pattern of 1, 3, 3, 2, 3, 3, 2, 3, 3, 2, etc. with the coefficients, the weights, and then there's this factor of 3/8 out in front, which is the namesake of the method. Okay, so now what's going on in here is some fairly high-level programming with Matlab, but recall that we need 3 panels, multiples of 3, for the cubic function underlying this method to work. Okay, and these 2, 3, 3, 2 patterns are coming from that cubic. So we first have to make sure that n is a multiple of 3. Okay, and this warning comes out if n is not a multiple of 3. We noticed that in the last example. What happens next? We define h. This defines the vector of x points that we're going to evaluate f upon. Evaluate them at f equals a plus h, onward up until x is equal to b. Okay. Now, how many points will that be? We would call them on the board x0, x1, x2, and onward through xn. Matlab starts at counting the first entry in a list, so we're going to have n plus 1 points. And so what's happening here with these 3 cases, okay, we're saying that x is the numbers a through b. There's a total of n plus 1 of them here. Okay. Total of n plus 1 points. Alright, and then here, take every third point, starting with x0, ending with xn. Alright, that's what the x1 is doing. And it turns out that x2 and x3 are doing the same thing. They're taking every point, the third point, here starting with xn, and ending with, well, what would this be? This would really be xn minus 2. Let's make this English. Okay. And then finally we're going from x2 through xn minus 3. X minus 1, excuse me. Okay, notice this order is not an accident. We're working sort of inwards. So we go to x1, xn minus 2, x2, xn minus 1. Okay, that might take a little while for you to sort through how that's happening. But basically what we're doing is there's this wraparound effect. So if I advance from x0 to x1, I have to advance from xn to xn plus 1. But xn plus 1 is out of bounds, so I jump back 3. And likewise here, this should be xn plus 2 if I'm following this pattern, but I subtract 3 to get this value here. Okay? And so it's always counting by multiples of 3. And why am I counting by multiples of 3? It's because there's 3 different coefficients. There's 3, 3, 2, 3, 3, 2, 3, 3, 2. And technically the first and the last values are different. They should be 1s, but there's this other way of writing things where I can subtract the endpoints, and that will give me the correct values everywhere as well. Okay, and so this is implementing the Simpson's 3/8 rule, where we're summing up f of every first of the third points times 2, and summing up every second of the third points times 3, and the third by another 3. Okay, so you might ask yourself, 2, 3, 3, hey, where's the next 2? Well, it's right here again. And then the one after it is here and here. Okay, so these are lists that we're employing, and they're going around and around as we go from the first, second, third point to the fourth, fifth, sixth point, 7th, 8th, 9th point, and eventually we'll end at the third plus extra point. Okay, so that's how the Simpson's 3/8 rule is working. And of course, the implementation is again very straightforward. If we have f already specified, a, b, and we just simply say that s is equal to Simpson's 3/8 rule with f, a, b, and n, and the value of r is known. Okay, so I'd like you to be able to do the same thing, make your own version of code just by basically copying and pasting this, making minimal adjustments to implement something like Boole's rule.